Okay, let us begin. Hello everyone, welcome back. So maybe a few general things before we get started. So first of all, I think I did a very bad decision to keep the assignment deadline at 10 a.m. in the morning. I saw more than 60 people submitted their assignments only in the morning, which means probably they were working all night, which was totally not my intention. Okay, I usually keep it at 10 p.m. on the day of the class, and it so happened that in oral, like because of that, like nobody showed up for class, like because the assignment deadline is on the same day. So moving forward, like so, I think based on these two experiences, like I'm going to keep the deadline the night before the lecture so that you finish it, sleep, and then come back to class. Okay. Now, the second assignment will be released tonight. So I had to delay it a little bit because there is 1 week of break next week. So I have to take care of the topics and move things a little bit around so that the Labor Day and the next week break doesn't affect the assignment. But in general, are there any feedback from the first assignment that I could consider just few hours before the release of second assignment? Yeah.
Maybe some external resources to the class notes would have been helpful, especially for question 4, because I don't think it was covered, you know, the whole all the materials needed to answer question 4.
So by question 4, do you mean like filling the missing values?
Yes.
Okay. Well, so the filling the missing value part was purposely without notes, like for you to think and come up with your own solutions. Okay. So like, let me see. I don't think we have any such questions in A2, so it's fine. But to give you my feedback, like so, like I did not expect you to come up with known methods. Like so, the question asks, how would you fill it, right? Like so, like you try to come up with your like that's the place for you to be creative and come up with your own solutions. So it was meant to be like that. Okay. But I think in general, probably we had less issues with the ML assignment compared to the oral assignment, which was the first time, and there are a lot of issues. Well, so the second assignment hopefully will be smoother than the first assignment. Okay. I just want to talk about like one, but there are a lot of good positive and negative feedbacks people are putting in the anonymous Google form. So this is another reminder for you. Like, so if you don't like something about the assignment or the course, also if you like something about the course, okay, so please go and write it in the feedback form, and I read it regularly. Okay, so there's one comment I want to discuss. I was not sure if I should not discuss or discuss it. Like, I think if I ignore the comment, then it means students think that I don't read it. So I'm going to discuss the comment. Okay, so there was one comment which said, like, there is not enough content in the course or course material. I think the word was course material. Okay, so I'm surprised. So, but at the same time, I don't want to ignore the comment because I don't want the student to feel that I neglected the comment. Okay, so I have made some extra improvements. So first of all, like there are lecture notes which are released like before the lectures. Like now I'm trying to do it at least a week before the lecture. Now, there are also textbook references, right? Like so, I think I kind of made this clear in the beginning of the course. I give the references in the textbook, but I will evaluate you only based on the lecture notes. Like so, if you attend the classes regularly without skipping, okay, with the intention of watching the videos later, if you attend the classes regularly and follow the lecture notes, there is nothing else you have to learn to do this class well. Okay, now, to make your learning process easier, I think I did this last year, but this time, because I'm too busy with teaching two courses, I forgot to do this. Like so, but I have added it now. So if you go to the course schedule page, like I have added self-assessment questions for all the lectures. Okay, so like first of all, like all the lecture notes are available in the first link. I'm not sure if many of you have noticed it. Like so, we put the links to the schedule, but they are all available here. And in fact, like I put them whenever the future lectures are ready. Okay. Now, I have added a couple of things. Like I have added the self-assessment questions, which are per chapter. Like, so if you go to the self-assessment question, like it is going to have some questions which will test your understanding of the chapters in the lecture notes. Okay. Now, other than that, I'm also putting all my class scribbles, because sometimes I write in class which is not there in the lecture notes, like once in a while. So I'm also putting the scribbles here. Okay. So, and you have recordings of all the lectures. Okay. So these are all the course material. Now, is there any other course material? Oh, other than this, like we have tutorials. Like, I know a lot of you skip tutorials because probably you knew Python and other things already. Like, but we had 3 tutorials, and we are going to have many more tutorials to help you with the programming. Okay, so is there anything else that I could do to give you more information? Okay, so my guess is if you don't come to class, if you skip classes with the hope that there is going to be recording, you miss out a lot, because I do talk a lot of things in the class which is not there in the notes. And I give a lot of announcements in the beginning and end, like which is not there in the notes, of course, right? Like, so I'm not sure like how disciplined you are to go watch the recordings, but I would not watch the recordings later, right? Like, so like if you say that you're going to watch the recording, most probably you're not going to do it. So it is just the best option for you to show up in class or join through Zoom, right? Like, so don't be dependent on the recordings. The recordings are really for people, it's for two types of people, okay? So for people who really cannot make it to the class because they are in different time zone or they are traveling and so on, right? And people who want to go back and watch the recording again and again to understand the concept, right? Like, so it is not for first time viewing. Like, so first time viewing should happen either in class or in the live Zoom class, okay? So I think if you do that more religiously, like, so you're going to do well in the course. Okay. Plus, please go and give more feedback. I'm always interested in improving the course. Like, so if you have any, if you like anything, like if you like the lecture notes or if you like the recordings, tell me that as well, so that I can improve on, I can do more of those things. Okay, so there is a question in the chat. Okay, this is a very good suggestion. I think it's based on your question. So next time it would be useful if we say a particular question is creative or like something that is out of the scope of the lectures. That's a good suggestion. I'm going to do that. And there is also another question: when are grades released? So my usual policy is to release the lecture, like release the assignment grades. Well, we try to release assignments grade like 1 week after the deadline, okay? But that includes late submission policy. So there are like 3 days of late submission. So if you, okay, we submitted it by Monday, right? So you submitted it today. So hopefully by next Wednesday or Thursday, you should have your assignments graded back, okay? So, well, it's good that they asked the question, because next week is a break, study break, I guess. So we won't be meeting next week. So once the assignments are released, like assignments are graded and released, like we are going to send a note in Moodle, and you will have 3 days to ask for regrade, okay? Just 3 days. Like, so you cannot, a lot of students come towards the end of the semester asking for regrade of the first assignment to get an extra mark, okay? We will not do that. So you have 3 days to ask for regrade. You go through your questions, find whatever questions you want to be regraded. There is an option in GradeScope to ask specific question for regrade, okay? And when you ask for regrade, last year we had some students who were really rude to just put a question mark in their request, okay? You should explain why you're asking for regrade. So if you just click regrade without any extra context, we don't know what is the reason for the regrade, okay? So if you think maybe the graph is correct, but the TA has not given marks for the graph, or like if you think your numbers are correct, but TS did not give marks for the graph, for the numbers, you have to explain why you're asking for regrade, okay? So you cannot just click regrade for the question without any context. So that is to help the TAs really to know what is the reason you're asking for regrade, okay? So the assignments are graded in a distributed way. So each question will go to a different TA. So the only way in which you can help the TA to regrade is by giving a proper context. Okay. Any more questions before we begin? Okay. Or late submissions. Okay, so there are a few more questions in the chat. Will you give answers for the assignments? Not for the assignments. Okay, so if you want to know the answer for any of the questions, you can always come talk to me during my office hours, or you can go to the TA's office hours. Okay, so like it's usually my policy to not give answers for the assignments, but you can come and ask us. Or late submissions submitted on grade scope. Yes, even if you are late, if you missed your assignment today, I think probably 10 of you have not submitted yet. So if you're taking one day late, you can still go and submit in Moodle and grade scope. They are all open until the final day of the late submission. Okay, so you can go and submit until, like, I don't know, 3 days or 4 days, like whatever the policy is. Then there is another question. It will be really nice to have detailed correction for assignment. Okay, so there are 110 students, I guess. Like, so, like, we will try to give reasonable feedback, right? Like, so, like, of course, there cannot be like paragraphs of text in the feedback. Like, so the reason why we are using GradeScope is to try to have a rubric which helps us to scale up giving feedback to all the 100 students. Like, so, well, another easier way could have been to make these assignments a team assignments, like, but I think you learn a lot by doing these assignments by yourself. These are very fundamental. Okay, a lot of questions about assignments. So let's get started. So first, maybe a quick recap, since it has been a week, right? So maybe for a change, can someone recap what we have done in the last week? I always give my recap, but does someone want to give a recap of like what we have seen in the last week? Okay. So no one remembers what we have seen in the last week. Is anybody in the Zoom? You can raise your hand if you want to talk to people in Zoom. But it's, yeah.
We talked about classification problems.
Sorry, can you please repeat?
We talked about classification problems.
Okay. Anything else? Yeah.
We talked about how to separate like the dataset dimensions using a hyperparameter to meet all the different questions.
Okay. Okay. Anything else that people remember from last week? So maybe I'll repeat because people in Zoom cannot hear. Like, so one answer was classification, like, and then like how the decision boundary looks in classification and so on. Okay, so maybe to quickly summarize, like, so I think we started with bias variance trade-off. Like, so we looked at how loss can be divided in, like, decomposed into 3 different components, right? So what are the 3 components in the loss? Anybody? Yeah.
Bias, variance, and noise.
Bias, variance, and noise, right? Like, so for any problem, like when you compute the loss, like there is going to be 3 components, right? Like, so your loss is bias square plus variance plus noise, right? So where we discussed that noise comes from the process itself. You cannot control it. You cannot do anything about it. So this part is the irreducible error. However, these 2 errors can be reduced, like, but there's a trade-off between bias and variance. If you go for highly biased models, they're going to have low variance. But then like high bias means there is too much restriction. So if you want to reduce the restrictions, like go for a low bias model, then it's going to have high variance, which means it is going to have problems with, in the way that it's going to be sensitive to data sets, right? Like, so after that, I think we started discussing about classification. So in classification, like we discussed about 2 class problems, K-class problem, like when you have more than 2 classes, like how do you set up your classifiers? Like it could be 1 versus 1 or 1 versus rest or a discriminant-based classifier, which is going to have a proper decision boundary, right? Like, and we also discussed the geometrical characteristics of like a decision boundary and classification problem. And finally, we talked about linear regression for classification or least squares for classification, right? So I think that's where we stopped. Okay. So towards the end, I mentioned that in the next week, like as in this week, we're going to talk about generalized linear models, like which are one step ahead of the usual linear models that we have seen so far. Okay. So for today's class, like so, we will be talking about probabilistic generative models. Okay. But we'll first start with a quick discussion of introduction of generalized linear models. Okay. Now, if you think about linear regression, right? So your model in linear regression was something like this, right? Like so, y of x is equal to w transpose x plus w0, right? So in this case, like this is for linear regression. Now we know that in linear regression, y is actually a real value. So it can take any number in the real line. So this particular y of x was a real number, right? And this is a very simple linear model. Like if you have a quadratic error loss, like least squares with a linear model, then you can differentiate, set it to 0, you get a closed form solution, all the nice properties. Okay. Now we want to do classification, right? So last week we looked at how to reuse this model for classification, which is basically you convert the class values into some numbers. If you remember, like we converted a 5-class problem into a one-hot encoding representation, like where each class have like 1 and the rest 0, right? So now this is my target vector. This is a real number. Well, it's kind of binary, but it is in the real line, right? Like so. Now I can just take my linear regression model and directly apply this for this classification problem, right? But then we also discussed that the problem with such an approach is you're not going to get 0 or 1 as the output. You're not even going to get something in between 0 or 1. You're going to get the whole real line as output, right? Like so, the output of linear regression for classification could be 5 or 7 or -6. It could give whatever number it wants because there is no restriction on like the range of output, right? Like so. Now, if you think about it, let's just consider a simple. Let's not go for K class. Let's go for a simple binary classification. Okay, you have two classes, 0 and 1. Okay, now I want to come up with a classifier which gives me either 0 or 1. Now, one way to do that is to come up with a classifier which gives me values between 0 to 1. Okay, let's say the classifier gives something like 0.2. Now, which class will you assign this? 0, class 0, right? Like if the classifier gives 0.7, probably class 1, right? Like you can have this threshold, which is like 0.5. Anything from 0 to 0.5 is class 0, and anything from 0.5 to 1 is class 1. Or in other words, this output that you're getting from 0 to 1 can be treated as probability of class 1. Okay? Now, if my y is equal to 0.7, then that means that the probability of class 1 is 0.7. So I'm going to call this class 1. Is that right? Now, similarly, if my y is equal to 0.2, then the probability of class 1 is 0.2 because this is lying more towards class 0, right? So then I'm going to call this as class 0. Fine. Now, I can construct such a 0 to 1 function by doing one small modification to my linear model. Okay, so this is what I'm going to do. So I'm going to take my linear model, okay, W transpose X plus W0. Okay, now I'm going to add some nonlinear function f. Okay, so this f here is a nonlinear function. Okay, now this function is going to put the output of the linear model to a specific range. Okay, so for example, I could have a function which takes the output of a linear model and squashes it into something between 0 to 1. Okay. Now, this output of y of x is going to be between 0 to 1. Okay, clear? So we are going to call this nonlinear function as activation function. Okay. Now, I have added a nonlinear function on the top of w transpose x plus w0. Now, can someone tell me if this is a linear model anymore? Is this still a linear model?
Yes.
So what is the definition for a linear model? Sorry?
It should be linear in parameters.
It should be linear with respect to its parameters. Okay, now, is this equation linear with respect to the parameters? So I'm making a nonlinear transformation of w transpose x plus w0. Yeah.
No, I would say no, because if the function is nonlinear in regards to the parameters
Yes.
x, it's nonlinear.
So this function is nonlinear with respect to the parameters. Okay. So this is not a linear model. Okay. However, what is interesting is this is not a nonlinear model either. Okay. So like if you look at the decision boundary of this model, it is going to still be linear. Okay. So let us verify that. Okay. Now let us take the decision surface. So usually the decision surface for the classifier is y of x is equal to some threshold, right? Like so y of x is equal to 0.5 in this case, but it need not be 0.5. So it is y of x is equal to some constant. Okay. Now, so we know that y of x is f of w transpose x plus w0. This is equal to some constant. Okay. Now I'm going to take this linear, like nonlinear function from f from the left side to right side. So w transpose x plus w0 is equal to f inverse of the constant. Okay. Now we know that f inverse of constant is some constant, right? So w transpose plus w0 is equal to constant. Okay. Now, my decision surface, right, is still a linear function of x, even if f is nonlinear. Okay. So in some sense, this is not as, like it's not very powerful. It's not nonlinear yet. Okay. So it's not a linear model, but its decision surface is still linear. Okay. So we're going to call such class of algorithms, like where you have, which is not linear, like because of the nonlinearity is introduced, but still the decision surface being linear, right? Like we're going to call them as generalized linear models. Okay, or GLMs. Okay, so GLMs have complex analytical and computational properties when compared to linear models. Okay, like however, they are still very simple class of algorithms. Is that fine? So we will also see some real nonlinear models today in the class, but first let's get started with generalized linear models. Okay, okay. So now we are going to see some examples for this kind of generalized linear models. Okay, so we will get started with probabilistic generative models. So if you remember from the previous lecture, so there are three ways in which one could design a classifier, right? So one is generative models. We have, so the basic idea in generative model is like you first learn probability of x given ck and probability of ck, right? And then you use these two entities to construct probability of ck given x, right? So that is, so you will use Bayes rule to come up with this, right? So that is generative models. Then we talked about discriminative models, where the idea is instead of trying to do this complex generative process, why don't I directly model P of ck given x, right? So that is discriminative models, like which is what we will see in the next week. So then finally there are discriminant based models, which is the idea of directly learning the class. So instead of worrying about the probabilities, okay? So you have a scoring function here, which is going to take X and tell you what class it is. Okay. So now probably in the order of simplicity, like we will like not of starting from complex and going towards more simpler models, like we will start with generative models today. Okay. So the basic idea in generative models is to compute P of X given CK, P of CK, and use that to compute P of CK given X, right? Like so. Now let's consider a two-class problem first. Okay. I have C1 and C2. Okay. I want to come up with a classifier, which is probability of. We know that in two classes, it is just 0 and 1. So it is enough to compute just P of C1 given K or P of C1 given X, right? So because P of C2 given X is nothing but 1 minus this value. So it is enough to compute just this. Now what is P of C1 given X? Like if I apply base rule, this is nothing but P of X given C1, P of C1 divided by P of X. Is that right? So just find base rule here. Now I can expand P of X. Okay, so this is P of X given C1, P of C1 divided by P of X given C1, P of C1 plus P of X given C2, P of C2. Okay, so if you don't know how I jumped from here to here, so what I have done is I have used this identity that P of X is basically summation over C P of right? So if I consider all possible C, then this marginalization is going to give me P of X. Okay, so now I'm going to do a little bit of restructuring here. Okay, so I'm going to divide the numerator and denominator by the numerator. Okay, so this becomes 1 by, so this and this are same terms. So it's going to be 1 by 1 plus P of X given C2, P of C2 divided by P of X given C1, P of C1. Okay, so nothing fancy yet. So now I'm going to add an exp and a ln together. So exponential of ln is the same value, right? It just cancels out. So I'm going to make this 1 by 1 plus exp of minus ln P of X given C1, P of C1 divided by P of X given C2, P of C2. Okay, so I added a minus so that I can swap the numerator and the denominator again. Okay, so now finally I can write this as 1 by 1 plus x of minus a, okay, where a is equal to ln of P of X given C1, P of C1 by P of X given C2, P of C2. Is that clear? Now, the reason why I did this transformation is because this particular form that you have is a standard form. This is called the sigmoid function. Okay, so now I can just write this simply as sigma of A. Okay, now if you have not seen sigmoid functions before, okay, a quick introduction to sigmoid function. So sigma of A is defined as 1 by 1 plus e power minus A. Okay, now this is also called logistic sigmoid. Okay, now sigmoid has a lot of nice properties, which is why we are using it in binary classification. Okay, first of all, it is a squashing function. It takes any value that it gets and it squashes between the range 0 to 1. So when you do sigma of something, you will always get values between 0 to 1, which is what we want for binary classification, right? Now, there are certain nice symmetry and inverse properties that sigmoid function has, like which is useful when we are computing the gradients, okay? So for example, it has the symmetry property sigma of minus A is 1 minus sigma A. You can verify this. I'll just put this as an exercise. Like it's just substitute the value of sigma. Like substitute the equation here. You're going to verify this easily. Okay. Now, also the inverse of sigmoid. Like what is A, right? A is sigma inverse, right? So it's basically ln of sigma by 1 minus sigma. Okay. Now, this inverse actually has a name, so we're going to call those as logics. Okay, so the thing that you have before taking sigmoid are called logics, and these are basically ln of p of c1 given x divided by p of c2 given x. Okay. Okay. Probably like I'm just listing the properties here, but we are going to use these like when we are computing the gradients. Okay. So now, what have we done so far? Like, so we started with base rule, and we constructed a sigmoid function for binary classification problem, right? Like, so now we can generalize this, okay? And let's see how to do the same thing, but for k-class problem. Oh, sorry. Okay, now for k greater than 2 classes. Okay, so when you have more than 2 classes, okay, okay, I think I might have, okay, so I think it should be of CS for here. Okay. Okay, so now when you have more than k more than 2 classes, right? Like, so then we want the probability for all the classes individually, right? Like, so if it is binary, you can do like just C1, and you're going to get C0 to be probability of 1 minus C1, right? So in this case, like we are looking for probability of CK given X, okay, which is again by base rule, probability of X given CK, probability of CK divided by probability of X, right? Now in this case, I have k different classes. So this becomes P of X given CK, P of CK divided by summation over J, P of X given Cj, P of Cj. Okay. Okay. Now, again, I'm going to restructure this. Like, so I'm going to call these as X of AK divided by summation over J X of AJ. Okay, where AK is going to be ln P of X given CK, P of CK. Is that clear? So now if you substitute this AK there, like X and ln will cancel out, you'll get the same equation again. Okay. Now what have I done here, right? Like, so now if I want to compute the probability of a particular class, then I compute this function. Okay. Now, if you think about this, this is basically some normalized exponential, right? You take exponential of a bunch of terms and you normalize it. Okay. Now, when you normalize things, you're going to get a valid probability distribution. Each of these values is okay, right? Like, so you're normalizing a bunch of things. You're going to get a valid probability distribution. Okay. Now, this is a multi-class generalization of logistic sigmoid. Okay, so this function also has a standard name like sigmoid function. Okay, so this function is called softmax function. Okay, now this is called softmax because this is a softer version of the max function. So how would you do max among k entities, right? Like you find whatever the maximum is, so you'll put 1 for that entry and 0 for the rest, right? So let's say I have 4 entries, then if I just compute the argmax, you're going to get 0, 0, 1, 0. Let's say I have a bunch of values, 40, 20, 10, 6. Okay. Now, if I have to compute the argmax, so which is the maximum value here? It's 40. So you would say this is the max. So argmax is going to be something like this. right? Now, softmax is doing it in a very soft way, in the sense you compute x of all these entities and normalize it. Okay, you're going to get some probability distribution. Okay, which is going to look something like this. Okay, 0. These are made up numbers. Okay, they might not match exactly. 0 0.2, 0 0.1, so 4, something like this. Okay. Now to make things easier, to make things appear at 230 here. Okay. So now this is the softmax output. Now if you compute the max of this, it's going to be this number, right? Now, if I have very high mass for the first class, okay, something like 99, 0.3, 0.3, 0.4. If I compute softmax now, then the softmax is going to look something like this: 0.999, 0.000, 0.0003, 0.000, something like this. Okay, so now you can see that this is very close to 1000. So it gets peakier as the confidence increases. Okay, so this is a soft version of argmax. Is that clear? Okay, so to summarize, like in terms of generative models, right? So we have two formulations now, like for the two-class problem, P of ck given x was given by sigma of a, which is a logistic sigmoid function, right? And for k-class problem, where k is greater than 2, we have P of ck given x is equal to x of ak divided by summation over jx of aj. Is that clear? Any questions so far? Any questions in the lecture? I think I answered the comments already. Any other questions? Okay, so now we are going to see an example algorithm, which is going to make use of this fact. Okay, so we are going to see our probably third algorithm for classification. Okay, so which is Gaussian discriminant analysis. A quick quiz, like so. When I say this is third, it means you have seen two algorithms for classification. Can someone tell me what are they? So what are the two algorithms you have seen so far for classification? Yeah?
We've seen k-nearest neighbors.
Sorry?
K-nearest neighbors earlier.
Yes, k-nearest neighbors.
And logistic regression.
Yeah, sorry what?
Logistic regression.
We haven't seen logistic regression yet. Just linear regression, right? So we saw how to use linear regression for classification. So we have seen k-nearest neighbors and just least squares. Okay. So today we are going to see a probabilistic algorithm, which is Gaussian discriminant analysis. Okay. Now, so the goal of Gaussian discriminant analysis is to compute somehow P of x given ck and P of ck, these two entities, so that I can apply Bayes' rule and use this formulation to compute P of ck given x. Is that clear? So this is what we are interested in, computing from the data. So give me a data set. I will first compute P of x given ck and P of ck. Then I'm going to use that and this equation to compute the class probability. Is that clear? Now, to compute these two terms, right? Like, so we're going to start with some assumptions. Okay. We cannot learn without any assumptions. We're going to start with some assumptions. It might sound restrictive, but we are going to relax these assumptions one by one. Okay? So the first assumption that I'm going to make is the class conditional densities, right? So P of x given ck, it is a class conditional density of the data, so P of x, okay? So P of x given ck, we're going to assume are Gaussian. So this is a very common assumption that you would make whenever you have some real valued entities, okay? So you would assume that the data comes from Gaussian. Now, The second assumption I'm going to make is all the classes, okay, share the same covariance matrix. Okay, when I say that P of x given Ck is Gaussian, it means this Gaussian has some mean and variance, right? So I'm going to assume that the covariance matrices of all these Gaussians are shared, which means if there are 5 classes, I have only one covariance matrix used by all the 5 classes, but they are going to have their own means. Is that clear? Okay. Now, I'm not sure how many of you still remember the density function for a Gaussian distribution. So now, in this case, we have a multi-dimensional Gaussian because there might be more than one features, right? So P of x given Ck is an n-dimensional Gaussian. Okay, so now d-dimensional Gaussian. Okay, so now the PDF is given by 1 over 2 pi power d by 2, 1 over sigma x minus 1 over 2x minus mu k transpose sigma inverse x minus mu k. Okay, where the mean is mu k and the covariance is given by sigma. Is that clear? Okay. Now, so this is what the probability of x given Ck is if I assume that things are Gaussian and the covariance matrix is shared. You can see that mean is labeled with k for class k. But sigma is not sigma k, it is just sigma because it is shared by all the classes. Okay. Now, this is just the determinant of sigma. Is that clear? Okay. So now let us consider a 2-class problem. Okay. So we already know that P of C1 given x for a 2-class problem is given by sigma of A, right? Where A is given by ln P of x given C1 P of C1 divided by P of x given C2 P of C2, right? I can actually simplify this A bit. Okay, so like I can just take A, which is ln of AB. Okay, so consider this as A, this as B. Can someone tell me what is ln AB? So what is ln AB? Okay, what is ln AB?
1 up plus ln B.
Sorry?
1 up plus ln B.
Ln A plus ln B, right? So, okay, it looks like we have to add a bit of more prerequisites for the course. Okay, so this is just ln A plus ln B, right? So I can write this as ln A okay, P of x given C1 by P of x given C2, okay, ln A plus ln B. Is that clear? Is that clear? Okay, so now I can substitute. I already know what is P of x given C1, right? So this is what the Gaussian assumption gives us. Like, so by Gaussian assumptions, we know that this is what P of x given C1 is. I can just directly substitute it here. Okay. Now this is equal to ln. Okay. I have 2 Gaussian distributions, P of x given C1 and P of x given C2. And here you can see that these terms, right? So they will cancel in both numerator and denominator. They're going to be same, right? So these terms are going to get cancelled. So you only have this x thing left. Okay. So it is going to be ln x of minus 1 over 2 x minus mu1 transpose sigma inverse x minus mu1. Okay. there's going to be divided by exp of the same thing for class 2, right? So since it is exponential, I can just put it in the top itself by saying plus 1 by 2 x minus mu2 transpose sigma inverse x minus mu2. Okay, so this is what the first term is. Plus, I'm going to keep the second term as such. Okay, now I'm just going to expand this term so that things get simplified. So this is, okay, first of all, ln and x will cancel each other, right? So we just, you see 1 by 2 in both the things. Like, so I'm going to take minus 1 by 2 outside. Okay, so I'm going to take minus 1 by 2 outside. So then this becomes, if I multiply this, becomes x transpose sigma inverse x minus x transpose sigma inverse mu1. Okay, so I'm doing this multiplication, then this multiplication, then this multiplication, and this multiplication. So there's going to be a lot of terms here, but don't worry about it. It's a very simple calculation. So this becomes minus mu1 transpose sigma inverse x plus mu1 transpose sigma inverse mu1. Okay. Now similarly, I can also expand this term. But remember, I took a minus 1 by 2 outside, so I have to add a minus here just to balance. So this becomes minus x transpose sigma inverse x plus x transpose sigma inverse mu2 plus mu2 transpose sigma inverse x plus, sorry, minus mu2 transpose sigma inverse mu2. Okay, plus ln of p of c1 divided by p of c2. Okay, so it looks like a lot of math, but we have really expanded things here, and we are going to cancel out things. Okay, so now you can see that this term and this term gets cancelled, right? So they are both same. So these are the terms where you have x square, right? So when you have x square, the model would have become nonlinear. Now we can see that because of the shared covariance matrix, these two things got cancelled. Okay, imagine I had separate covariance matrices for these classes. Okay, so I had sigma 1 for class 1 and sigma 2 for class 2. So then these two things would not have got cancelled because the first one is x transpose sigma 1 inverse x, the second one is x transpose sigma 2 inverse x, right? Like so then it will not have got cancelled. So you would have had a nonlinear model. So now because of this shared covariance matrix function, we have a linear model here because all the other terms that you see here, they are just function of x, right? So now I can write this, I can expand this further. So this is basically x transpose sigma inverse mu1 minus x transpose sigma inverse mu2, okay, minus 1 over 2 mu1 transpose sigma inverse mu1 plus 1 over 2 mu2 transpose sigma inverse mu2. Okay, so plus ln p of c1 by p of c2. Okay, so I have also brought the minus 1 by 2 inside. Okay, so now I can take this and restructure things a bit. Okay, so in these two terms you have x, right? So you don't have x in other terms. So this is basically x transpose sigma inverse of mu1 minus mu2 minus 1 over 2 mu1 transpose sigma inverse mu1 plus 1 over 2 mu2 transpose sigma inverse mu2 plus ln p of c1 by p of c2. Okay, now so this whole equation I can simplify it as some w transpose x plus w0 once again. Okay, however, my w transpose and w0 are going to be very complicated. In this case, this is going to be my w, okay, and this whole thing is going to be my w0. Okay, so my w is basically sigma inverse mu1 minus mu2, okay, and w0 is minus 1 over 2 mu1 transpose sigma inverse mu1 plus 1 over 2 mu2 transpose sigma inverse mu2 plus ln P of C1 divided by P of C2. Okay. Now I can write the equation P of C1 given X as, if you remember, it was sigma of A, right? We have just computed what is A, so this is sigma of W transpose X plus W0. Is that clear? So what did I do here? Like, I'll probably summarize and then we'll take a break. So we started with the assumption that P of X given CK is going to be Gaussian, but we had another restriction that all the Gaussians are going to share the same covariance matrix. Okay, so then all you have to do is substitute the Gaussian's distribution function, like in P of X given CK, like in the base rule, okay, P of CK given X. And finally, we arrived at this form, which looked very similar to the linear model. Okay, however, W0 and W are a bit complicated. So final form that we have for GDA, this is the equation for GDA. Okay, is P of C1 given X is equal to sigma of W transpose X plus W0. Now, if you have to implement GDA, okay, now you will be implementing this equation, which means you need W and W0, which means you'll be implementing this equation, these equations, right? But there are certain things that you need to compute these equations. So what are they? Or in other words, what are the parameters of GDA model? Anybody? So what are the parameters of this GDA model so that you can learn them from the data and compute the probabilities? Okay, there are some answers in the chat. Yeah.
Are any of the W, W0, are any of the constants we have here, are any of those not parameters?
Oh, that's a good question. They are all parameters, right? So both the W and W0 equation has a lot of terms. They are all parameters, right? Like, can you summarize what are all the parameters in the system?
Well, I guess the covariance.
Yes. So are they the only parameters? Like, so you have the means, right? So mu1 and mu2, right? So these are the parameters, okay? And then you have the covariance, sigma. Anything else? Anything else? Is that all you have in the two equations? Yeah?
C2, because C1 is a parameter of the function, and C2 is under the.
What do you mean with C2? C2 is just a class 2, right? Yeah.
Probability of C1.
So this one, right? The P of C1 and P of C2. Somebody has to give you the P of C1 and P of C2. These are prior probabilities of the class, okay? So this GDA algorithm, okay, to summarize, has a bunch of parameters that we have to learn. So GDA has mu1 and mu2, which are the mean of these two classes, right? The class conditional densities. And then the sigma covariance matrix. Then you have P of C1, then you have P of C2. Okay. So if you learn these things, then you can use the equations that I wrote in the previous slide to compute the class probabilities. Okay. So probably we will stop here and take a 10-minute break and then talk about how to learn these parameters from the data. Okay. So we will continue at 1:50.